So I'll start right away. Hi, good afternoon, everyone. I'm Jinwoo from KAIST. Today, I'm presenting our paper, Kova, where we propose a new video analytics pipeline that addresses the bottleneck of prior works by exploiting the compressed domain analysis. So according to a survey, video data is taking up 82% of the global IP traffic as of 2022, but this number is only growing. So many emerging applications like smart home cameras, AR, VR, or UAV drones, autonomous driving cars, and so on rely largely on the video data. So in the future, video data will be generated from diverse sources and scenarios. And as more video data are generated, building better ways to process and extract insights from the video has become important. In that sense, we aim to optimize the video analytics system, which is a tailored system to analyze video and answer user query. So for example, if a city planner is interested in a trend of a traffic at a specific intersection, he can ask the system to count how many cars there are in an hour and use the answer to make his decision. Also, the recent advancements in the neural network field provides a useful tool for video analytics, which is the highly accurate object detectors. So here's an example of how object detector can help analyze video. So here, user is querying about the sequence of video, and he wants to know when a car appears. So the video analytics system can first apply the object detector to its frames. And for example, in frame 2, it found a person walking by, and in frame 3, it found the same person and a new car. And once it's done running the object detector, it can process this result to answer the query. So as you see here, this object detector is working as a major component in the system, but at the same time, it imposes a significant challenge. And the challenge here would be that DNN-based object detector requires heavy computations. So YOLO, for example, would run like 11 hours to process 2-week-long video. So the prior approaches recently made in the database field introduces 2 new concepts to address this challenge. The first is to use a simple neural network that is specialized for the user query. And the second is to build a cascade architecture where a pipeline constitutes of multiple classifiers that trace accuracy and performance. I'll explain these 2 concepts in more detail. So first, the specialized neural network. So the prior works first focused on the reason why object detectors are so slow in the first place. And the reason for that would be that object detectors have very complex model architecture because they were designed to solve a complex task, which is to determine location and the labels of every appearing objects in the frame. So in order to reduce the computation, they wanted to simplify this task to an easier one. And one information they used was that they already know what user is looking for. So in this example, the user is interested in finding cars. So instead of using this large model that finds all kinds of objects, even the one that user's not interested in, they train a specialized neural network that's specifically trained to determine if there's any cars in the frame or not. So this model has only one value, and if the value is 1, it means there is a car in the frame, and if the value is 0, it means there's no car in the frame. And the values between 1 and 0 can be interpreted as how confident the model is. And the second approach that they make is to build a cascade architecture out of this specialized neural network. I'll be using an example to explain this concept. So cascade architecture first applies the specialized neural network to all of its frames. So first, for the first frame, the return value was 0.05. That means the specialized neural network is sure that there is no car in the frame, so we can label this frame, the prior works can label this frame as not having the car and it's not the frame that the user is looking for. And say for frame 2, the return value was 0.48, which means the specialized neural network was not so sure about its own decision. So instead of labeling this frame according to this value, they apply the heavy object detector for this frame. And as a result, it found the car in it, and they can finally label this frame does have a car and is one of the frame that user is looking for. And say for the third frame, the return value was 0.97, which means that specialized neural network is confident that there is a car in the frame. So in this case, we don't have to run, they don't have to run the object detector to that frame, and we can still label it as the frame that user is looking for. So one thing to note here is that the only frame that went over the object detection was frame 2, and for frame 1 and 3, it was able to skip the computation. However, we noticed two major limitations from the prior approaches. The first is that there is a bottleneck from the decoding. So despite the prior approach achieved high speed up by filtering out the frames going into the object detectors, in the real world, the video data actually are stored in a highly compressed format that requires decoding, and as modern video codecs are very complex, they run in much slower throughput than the later pipeline and works as a severe bottleneck. And the second limitation they have is they lack the support for the spatial query. So recall in the previous example, running object detector on one of the frame was enough to answer the question. However, this time the user's interested in where a car appeared. So for frame 2, we have the bounding box information, so we can answer the query right away. But for frame 3, we don't have the information about the bounding box. We know the car is somewhere in the frame, but we just don't know where it is. So the prior works cannot support the queries that require spatial context. And to this end, we devised Kova, shorthand for compressed video analysis. And the main idea of our work is to extend the scope of the cascade so that we filter out frame before decoding, not after. So this in turn reduces the number of frames going into the decoder and addresses the decoding bottleneck and offers 4.8 times end-to-end speedup. And at the same time, we designed this filtering scheme in a way that preserves the spatial context so we can support the spatial query. The followings are the internal stages in Kova, and I'll explain each stages one by one. First, to the track detection stage. So track detection stage, the goal is to find the tracks of moving objects without having to decode any frames. However, not decoding any frame means that video data are still stored in the compressed format. Then how can we find objects from a compressed video? So in order for me to explain this, I'll briefly have to go over how modern video codec works. So since 1995, when MPEG-2 was invented, several kinds of codecs has been invented. But they all share the same key algorithm, which is the block-based compression. And the way the block-based compression works is to first divide the frames into a grid of blocks, which they call macro blocks. And when saving each of the macro blocks, instead of saving all the RGB pixel values, they look for a similar looking block from a previous frame and saves this relative position as a vector. And this compression metadata is called motion vector, and the scheme works very effectively as the frames in the videos are captured in high frequency, like 30 frames per second. That having said, now have a look at this picture. So this picture is showing an example of motion vector field. And if we look closely, we can see consistent patterns appearing where moving objects are. But at the same time, similar patterns can also appear due to the noises from lightings or the ripples in this case. So the challenge here is to find the moving objects from this noisy compression metadata. And the solution that we came up with was to use a neural network-based algorithm. So we devised a neural network called blobnet. As the input, the blobnet takes in 3 kinds of compression metadata, which of the latter 2 we omit the details in the talk. And for the model architecture, we searched among the encoder-decoder architecture, which are known to be effective for denoising tasks, and selected a neural network called temporal unit, which was originally designed for video instance segmentation model. Also, we add an additional embedding layer as the compression metadata does not come in the scalar value as RGB pixel does, so that the neural network can learn the different compression metadata. And finally, for the training labels, they are generated using the background subtraction techniques running in the pixel domain. And the following sequence is the result of our trained blobnet. And as you see here, the noises from the ripples are gone, and only the objects of our interest is being captured. Also note that we use the term blob to define the region where moving objects appear, and that's where the blobnet got its name from. So by running the blob nets, we were able to find the blobs. However, blobs are just still binary masks consisting of zeros and ones. So in order to associate blobs into a track, we apply sort algorithm, which is one of the state-of-the-art tracking algorithm known to deliver robust tracking result at low computational demand. And finally, at this point, we are able to find the tracks of moving objects in the video without having to decode any frames. And our next stage is frame selection. The goal of frame selection is to select the minimal frames to decode. But why would we need to decode any of the frames? So from the previous track detection stage, we were able to find the trajectories of each object. However, we haven't decoded any frames yet, so we never got to see what they really look like. So we don't know if these objects are a car, or a person, or a bus. And to figure that out, we need to decode some of the frame to get to see it. However, the question here is that, can we just pick any of the frames to decode? And the answer to that question is no. And the reason is that not every frame has the same decoding cost. So recall in the previous example, how macroblocks are compressed by referencing its previous frame. So in order to decode one frame, we would need to decode its previous frame that is dependent on first. So for the first frame of the video, it didn't have any other frames to reference, so this can be decoded by itself. But think about frame 2, who's dependent on frame 1. We first need to decode frame 1, then start decoding frame 2 in order to see the objects appearing in the frame 2. So that would add up the cost to decoding 2 frames. And for frame 3, which is dependent on frame 2, and frame 2 is again dependent on frame 1, so that adds up the cost to 3 frames. And this dependency linearly grows and goes on. And minding this dependency, we develop a dependency-aware frame selection algorithm using the track detection result. And the basic way that this algorithm works is by tracking when an object enters and leaves the scene. So in this example, object A enters the scene at frame 40, then object B enters the scene at 120, object C enters the scene at 140, and later at 170, object A leaves the scene, and finally at frame 230, object B leaves the scene. And at this point, our algorithm is able to find the range of frames where we can see all 3 objects at once and find the optimal frame to decode that minimizes the decoding cost. Note that in reality, this dependency doesn't scale from a specific certain point, and they break, and this pattern is repeated. So please refer to our paper for a more detailed version of our algorithm that covers all the edge cases. So now that we selected the frame to decode, we can decode it and apply object detector on it and get the result as such. And to our final stage, label propagation. The goal of the label propagation stage is to combine the results from the previous stage to label the track. And the way we do it is by first retrieving the blob location at the same timestamp of object detected frame. And by calculating how much they overlap, we can assign the labels to the track. And the assigned labels are propagated throughout the track, even to the ones that are not decoded. So that finishes the description of Kova. To summarize, the first 2 stages of Kova works in the compressed domain to perform filtering and extract tracking information. And the label information is extracted from the pixel domain. And our last stage, label propagation, combines those 2 information to answer the user query. Now I'll talk about our evaluation setup. We used 5 videos in total, 4 of which were from the prior works and 1 newly collected video from YouTube live stream. They're an average 28 hours long. We evaluate Kova on 4 different queries, which of the first 2 are from the prior works. The binary predicate is a query to find the timestamp where a certain object appears, and the global query is a query to count the number of certain objects appeared throughout the video. And the latter 2 queries are spatial variants of the first 2 that Kova is able to support. The evaluation was conducted on a server with 2 Intel Xeon CPUs and 1 NVIDIA RTX 3090 GPU. Now let's first look at the graph showing the end-to-end system throughput. Kova achieves 4.8 times higher throughput in average compared to the prior works, and the speed up ranges from 3.7 times to 7.1 times depending on the dataset. This behavior is due to the amount of filtering performed varies according to the content of the video. So for the videos where objects appear more frequently, we'll need to decode and apply object detection more often to identify the labels. The following table shows the actual rate of filtration achieved for decoding and the object detection inference. So in average, Kova reduces decoding over 80% and inference workload over 99%. Such high filtration rate is the key behind the throughput improvement of Kova. Also, note that the reason why the filtration rate for decoding is much lower than the inference rate is because the decoding includes the frames decoded due to the dependency, but not for identifying the object labels. Next, we analyze the bottleneck of our new Kova pipeline. The bottleneck is represented in a bar with the shades and the letter B. Note that in this experiment, the performance of each component cannot exceed its previous component, and that's why these bars with the same heights keeps appearing. According to the result, the bottleneck of Kova differs across dataset, affected by the filtration rate that we just saw in the previous slide. And one more thing to note is that the compressed domain filtering introduced by Kova never becomes the bottleneck in any cases, which proves that they were designed in a way to meet the throughput requirement. Now I'll report the implication on accuracy from Kova. So in general, we observe modest level of accuracy degradation comparable to the prior works. And for example, the degradation on binary predicate query falls within the range of 10 to 15% with the GR mean of 12%. So considering the application of Kova, where we aim to process a large corpus of video at very high speed to extract the high-level insights, we believe this amount of approximation is tolerable. So in conclusion, we propose a novel video analytics pipeline that introduces compressed domain analysis and achieves 4.8 times end-to-end speedup and can still keep the support for spatial queries. Our implementation is open sourced and has gone through the artifacts evaluation process. So if you're interested, please visit our GitHub repository. And thank you for listening, and I'll be happy to answer any questions.